For our second example, it says, show that the substitution y equals ux transforms this second order differential equation into another second order differential equation. So this example is a little bit different from the previous one. Now, this second order differential equation is something that we know how to solve because it has constant coefficients compared to this one, which is why we're doing the reduction. So we're going to start out with the substitution we're going to make. And remember that your aim is to get rid of the y's and change them to u's. So we're getting rid of the dependent variable, changing to another variable, which means this y needs to go, and we're going to substitute it out with the ux. This dy dx needs to go, which means we need to find dy dx from this. Now, bearing in mind that u is a function of x, we will have to use the product rule. So dy dx is equal to, keep the second, differentiate the first, plus keep the first, differentiate the second. So our first derivative, or dy dx, is x du dx plus u. We will also have to change the d squared y dx squared. So we're going to have to differentiate the dy dx. So we're going to have to use the product rule right here, which says keep the second times differentiate the first, plus keep the first times differentiate the second. And then we need to differentiate the u. That gives me x d squared u dx squared plus 2 du dx. Right, so we have all that we need to substitute out the y's. So we're going to say sub into differential equation. So that gives me x squared times this thing here. So x squared times plus 2x times 2x minus 1 times what we got for dy dx plus, what is this, 5x squared minus 4x plus 2 times y, which is ux, equals 0. And so now it's just a matter of expanding out all right, some more expansion. That is 4x cubed. Yep. this is pretty long. All right, let's see if we can simplify a bit. Looking at what we're trying to get to, this, okay, no, let me simplify this statement first. Let's look for the like terms and add them or subtract them. So we're going to have x cubed d squared u dx squared. And then let's look for the du dx. We have 2x squared minus 2x squared. So that's gone, or those are gone. We have a plus 4x cubed du dx. All right. Then we have 4ux squared here. And I see a subtract 4ux squared. So those would be gone. I see a negative 2ux plus 2ux. So those would be gone as well. And I see a 5ux cubed. So that would be plus 5ux cubed. Okay. And then we're going to divide through by x cubed, because if you look at what you're trying to get to, the d squared u dx squared doesn't have a, well, it has a coefficient of 1. So we're going to divide through by x cubed. And we get exactly what we were trying to get to. So I'm going to say shown. Okay. And that's part A. We were able to use the substitution given to reduce this second order with non-constant coefficients to a second order with constant coefficients. B now is asking us to find the general solution for u. So we're going to use our knowledge of solving second order differential equations with constant coefficients to solve this for u. So, like before, we would form our auxiliary equation. In this case, we will not be able to factorize it, so we will use our quadratic formula. That gives me negative 4 plus or minus the square root of 16 minus 20. That's negative 4. That would be root 4i. That's 2i. All right, which means yc, oh, not yc, uc. We're solving for u. So uc is equal to a e to the negative 2x cos x plus be to the negative 2x sine x. That's your uc. Now looking at the differential equation, it's homogeneous because we have 0 on this side, which means we don't have a up, which means our u is simply the uc. And the question ends there with us finding u, but it could have taken it a step further and said find y, because remember the differential equation was given in terms of y. But it would be really easy to find y, because you'll recall that y is equal to u times x. So your y would be equal to whatever you found u to be, which is this thing here, times x.